Mr. Sands.
Yeah.
I'm looking at these
My dog toys.
dog toys.
Yeah.
Do you like have a dog?
I used to. We found out we were having twins.
Oh, so you decided no dogs.
No, we farmed her out.
Yeah. Well, these are kind of cool. I like these. It's like this actually kind of looks like chemical.
No, that's why I got them.
Yeah, this is like. Oh, I like this one.
It's just a perk, yeah. Octahedral.
Nice octahedron, folks. This is the octahedral shape. How cool is that?
Yeah,
and this is a tetrahedron, man.
Actually, it's tetrahedral. This is a tetrahedron.
That's actually true. Yeah. Well, I was checking to make sure you understood that,
I
and apparently you do.
Yeah, apparently.
Yeah, I'm pretty
make
impressed.
Nice hats too. My kids like to do that.
Yeah, Hatland. Yeah. Okay.
Yep.
Well, folks, what we're going to do today is we are going to be learning about two main topics: resonance and the Vesper model of the atom. Right, I have no pin now. What happened to my pin? Control P. I have pin now. Very good. Okay. I could not get to work. All right. So, we want to talk about resonance. Tell me about resonance, Mr. Sam.
Well, that's when you can have more than one valid Lewis structure for a particular substance.
More than one valid Lewis structure. That's very cool. So how's that definition of different than resonance structures?
Well, I guess I'd probably define resonance structure.
I'm thinking this is actually the definition of this.
Yeah, resonance, basically you've got electrons that are kind of flying around. You can, let's just do an example. Let's do the nitrate ion.
Yeah, I think it's probably good to do an example. So let's do an example, and let's do, like you said, the nitrate ion. Now we've drawn the Lewis structure of nitrate before, so I'm not going to, take the 5 plus 3 times 6 plus 1. So you should be good at this now. So I'm just going to draw the structure of nitrate. So nitrate looks like this. You have 4 electrons on that top O. You have 6 electrons on this O, 6 electrons on this O. And since it is an ion, you need a bracket and a charge. And so Lee, make sure you have your charge. All right, but could we draw more than one structure?
We could, because right now you've got the double bond going up to the oxygen up on the top, but it could just as easily have come from one of the oxygens, one of the other oxygens.
So I could draw it like this and put the O, the double bond on the O that's in the bottom left corner, as I've done here. Or I can... Or I think there's probably another one, Mr. Sams.
Yeah, you could go to the other oxygen, the one on the right there.
Yeah, so I could do the one on the right. Put it down here just to make more space. All right, takes the 1, 2, 3, 4, 5, 6. Okay.
All right.
And negative 1.
Charge. Yeah.
I got the charge. Lee, did you get your charge? Don't forget the charge.
Yeah.
All
so
right.
basically that double bond is... Ooh, this is not correct, Mr. Bergman.
Oh, this should be a single bond here. Yep. Okay.
That double bond is it's kind of scooting around. I mean, you could say that it's resonating from one oxygen to the other. So the electrons there are they're really kind of in all the places all the time. They're just kind of scooting around in there. And all of them are valid Lewis structures, and the electrons resonate, if you will, from one oxygen to the other.
Basically, yeah, this second bond right here, right there, whatever, it can move from one bond to the next. So there's actually something that's very important to understand about resonance structures, and that is that if you were to look at the nitrate ion, actually, maybe we should have a little conversation first about double and single bonds. If I had a single bond versus a double bond versus a triple bond, the single bond would be the longest bond, and the triple bond would be the shortest bond. Forget the N right here. And then, of course, the double bond would be
in between.
In between. It also, the single bond would also be the weakest bond, and the triple bond would be the strongest bond. And, of course, the double bond would be in between. So the interesting thing about nitrate, though, is if you look at nitrate, let's change the color maybe. About the nitrate is if you were to look at the structure, you would expect to see a double bond and 2 single bonds, right? So you'd have a short, strong bond, and you would see, maybe I'll now draw the structure. You would have a short, strong bond and 2 weak, long bonds, right? But that's not the case. What is the case?
We've got 3 bonds that are the same.
We've got 3 bonds that are the same. They're all actually the same. You'll say, well, a single and 2 doubles. But the answer to when we talk about resonance is technically the actual Lewis structure is the average of all of the resonance structures. I think an easier way to look at this is to think of the nitrate as having a single bond to each and a third. So maybe we do a dashed line. It's almost easier to think of that. And what really is going on is those electrons, because what actually, these are the O's, and each of these is like a bond and a third in this case, a third. So yeah, so each of these is the same strength. And so, Mr. Sams, if you were to look at the bond in the nitrate ion, how would you explain its length and strength compared to a regular single bond or a regular double bond?
Oh, well, it's going to be shorter and stronger than a regular single bond, but it's going to be longer and weaker than a regular double bond.
So it's going to fit in kind of right here.
Yeah.
So it's not as strong as a double bond, and also not as short as a double bond. So it's an intermediate between. And if you think of it as a bond and a third, that tells you it's a little bit stronger than a single bond. Oops, didn't circle very well. Okay? Does that make sense? So that's resonance. You'll be asked to draw lots of resonance structures, and there's lots of them that can be quite interesting, but we'll let you have at that. Another important concept is to discuss the concept of a formal charge. Oh my gosh, formal charge? Sounds like you like a formal wear for the prom date.
This is the charge with a bow tie.
Yeah, the charge with the bow tie. And these are essentially the rules. You take the number of valence electrons typically associated with the atom, subtract the total number of electrons, subtract the number. Now, when you're trying to determine which structure is best, you want your formal charges closest to 0. Now, you should copy this down. All right, it might already be in your handout. And then we need to do some examples. All right, the classic example in formal charge is the sulfate ion. So if you were to draw the Lewis structure of the sulfate ion, almost everybody would draw it just like this. I'll draw it for you. Again, I'm not going to take the time to tell you how to draw that. Play the game. Add up the electrons and distribute them. I happen to just know the structure in my brain cells. I know way too much about some things, don't I? This is what you would say, right? That obeys the octet rule. Everyone's happy. Everyone's got 8. We're happy, right? Well, let's assign formal charge now. We want to assign formal charge to every single one of my atoms. Now, what you do is you take the number of electrons normally associated with the oxygen, or for example, up here. Oxygen normally has 6.
Right.
And then you take the number of electrons around it. 1, 2, 3, 4, 5, 6. And then the bond counts as just 1. So you say 6 minus 7. So the charge on this O, or the formal charge, would be negative 1. And if you look at each oxygen,
They're all the same.
They're all the same. So they would each have a formal charge of negative 1. Does that make sense?
It does.
Now the sulfur, though, normally has 6 electrons assigned to him. And you would subtract each bond. Each bond counts as one number, 6 minus 4. You see what I'm doing from the rule set right here. Subtract the actual number of electrons around the atom. Subtract the number of bonds. I'm doing that. 6 minus 4 is positive 2. So the formal charge on the sulfur is positive 2. The formal charge on the oxygens are negative 1. The problem with those numbers is they are not very close to 0.
Nope.
There is a better way to draw these sulfate ions. So let me, and this is going to violate the octet rule.
But sulfur can do that because it's in the third period.
Right, and we talked about that last time, violations of the octet rule. If I were to draw this Lewis structure like this,
Okay, we still have 32 electrons, so we're still...
I have not violated anything. I've just made 2 double bonds and made a 2 negative charge here on this one. And now I'm switched to red. Now what is going to be, there are 6, you still, for the oxygens, you'll say 6, right? But then minus 1, 2, 3, 4, 5, 6, 7. So this will be 6 minus 7, so he would have charge of negative 1. The ones with the single bonds.
Right, just like it did last time.
Just like the last time. But for this oxygen, this outer oxygen out here, you'll do 6 minus, and then you've got 1, 2, 3, 4, 5, 6. So 6 minus 6 is 0, right? And for the sulfur, it will be a 6 minus, and there are 6 bonds around him, 6, which is 0. Now, the rule is the structure that yields the closest to 0 formal charge wins. Well, obviously, picture 2, if you will. and I'm circling or whatever, is a better picture.
Yep.
Therefore, the formal charge, this is a better picture of the sulfate ion than is this. And actually, you would have resonance with this, wouldn't you? Because you could move the double bonds onto another atom.
They could go, they could go to the up
top
and down
and
oxygens,
exactly.
if you will.
So you have resonance actually with this. An interesting thing. So that's a good example. Another example that's pretty interesting to talk about is HCN. Hold on. All right, I figured it out. If you were to draw the Lewis structure of HCN, one way you could draw it would be like this. And if you were to assign formal charges, hydrogen would be 1 minus 1. The hydrogen would be 1 minus 1, so he'd be 0. He's pretty happy. The carbon, though, would be 4 minus 2, so he'd be positive 2.
Right.
So, and then the nitrogen would be 5 minus 1, 2, 3, 4, 5, 6, 7, so that would be negative 2. So that's not very good. So, and you probably realize, folks, that if you were to draw the Lewis structure of HCN, you would actually have a triple bond. And this one you might say, Mr. Sams just pointed this out off camera, that this doesn't even obey the octet rule. But this one would. You'd say 1 minus 1 is 0, 4 minus 4 is 0, and 5 minus 5 is 0. So this is the correct Lewis structure for HCN. Another good example that would be available, let's not do ClO3. And then the last example I want to talk about is OCN negative. O gets 6 plus 4 plus 5, that's 10, 15, that's 16 electrons, right? So you could do O, and then you could do C, and you could do N. So I've got 2, 4, 6, 8, 10, 12, 14, 16. So that's one structure.
Yep.
Another structure would be O, C, N. 1, 2, 3, 4, 5, 6, 7, 8. And actually brackets around each, of course, because this is an ion. Forgot my charges there, Lee, didn't I?
Yeah.
Or you could do O, triple bond C, single bond N, and then do 2 here, 1, 2, 3, 4, 5, 6. So each of these are the valid Lewis structures. Oh, and one more. What's the other one? I need a double bond. I already did the double bond. That's
yep.
it. Okay,
You
so
forgot
now
your charge, Mr. Bergman.
I forgot my charge. Lee, I tell you, you're rubbing off on me, I tell you. All right, so now what I want to do is evaluate which of these is the best structure. So for the O starts with 6. So 6 minus 2, 4, 6. So this would be 0 right here, right?
Mm-hmm.
And the carbon would be 4 minus 4, which would be 0. And the N would be 5 minus 6, which is negative 1.
Okay.
That's pretty good, actually.
That's not too bad.
You have to have the total charge add up to negative 1 since this is an ion. So this is actually a very good structure. Well, let's do the second one. This will be 6 minus 7. That'd be negative 1.
Mm-hmm.
And this would be 0. And this would be, these are 2 electrons, not nickel. This would be 5 minus 1, 2, 3, 4, 5. 0.
Okay.
That's pretty good, too. So
Yeah,
is one of those better than the other?
I think they're equally valid.
They're equally valid. How about this one? So we do 6 minus, for the oxygen, 6 minus 1, 2, 3, 4, 5. So that'd be positive 1, right?
Yep.
The carbon would be 5 minus, or 4 minus 4 is 0. All right, he's pretty happy. And this would be 5 minus 7?
7, yep.
Negative
So
2.
Still adds up to minus 1, but not everybody is close.
So this structure is really bad. It does not. So this one is our invalid structure. So the real resonance structures, if you will, of OCN negative is the average of these two.
Mm-hmm.
So this one is no good because from our formal charge ruling tells us that. Where this one right here, these two, pardon me, are good. Make sense?
All right.
All right. Good. All right. Vesper. Vesper.
Vesper.
I like that. Vesper. I like this. Yeah.
Because the E's in the wrong spot.
All right. Is it in the wrong place?
No, it's right there, but
Oh, okay.
it'd be Vesper.
What does Vesper stand for?
Valence.
Oh, hold on. I'll write it down.
Oh.
Gotta
get
change
his
colors.
pen.
Valence.
Shell.
Shell.
Electron.
Electron. That's a big E.
Pair.
Pair.
Repulsion.
Repulsion.
And it's a theory, so we put the theory.
Theory.
Vesper theory.
So the Vesper theory. This means that
Vesper.
valence electrons want to stay as far apart as possible.
Yep.
You see, electrons, folks, have like the same charge.
They're all negative.
They're all negative. And so, of course, if everything's negative, they,
Repel.
because they like to stay with. So why do they stay apart?
Because opposites attract and likes repel.
Because likes repel. Repel?
Repel.
Repel. I still...
You're pretty good at
Repel.
There you go.
I think I was trying to spell what I was trying to say with the
Repel.
funny accents, and then
Repel.
came out. Yeah, repel.
Now.
All right. So it's all about something called effective pairs. We're going to call effective pairs clouds.
All right.
Now, there are two kinds of effective pairs. An effective pair can just be a pair of electrons.
Unbonded.
Unbonded. So we're going to call this an unshared pair. Or it could be a shared pair.
Right.
Actually, it could either be a single bond, a double bond, or a triple bond.
Right.
These also count as
One cloud.
or actually one effective pair.
Right.
Or we're going to say one cloud. So if it's a single, a double, or a triple bond. So yeah, so these count as one, and these count as one. Okay? It's very important when we're trying to understand the shapes of atoms and molecules. Now you've got a paper. Now this one's kind of got some pictures missing on purpose. Excuse me. This is, we'll call for all intents and purposes, the shape paper. It has all of the shapes that you'll have to know. Now if you took chemistry last year, you learned about some of the shapes, which is cool. However, there are more shapes this year. So we add quite a few more shapes this year, and we want to now learn about the shapes of the molecules. Now, the number here is the effective pairs or the clouds. I think your paper says clouds, and mine's kind of missing it on here. So this is the clouds, or the number of effective pairs. And so if you have 2 effective pairs versus 3, 4, 5, or 6, it changes the different shapes that you can have for a molecule. So the first shape that we want to talk about is the linear diatomic shape, okay, which has how many clouds?
2 clouds.
2 clouds. First of all, I just realized Mr. Sam's caught that this is a typo here. This is a linear triatomic. Okay? So let's fix that before we move on. All right, so folks, I have 3 atoms right here, the styrofoam balls. And of course, the VSEPR says I need to keep the clouds as far away as I possibly can. So
Yep.
I'm thinking this looks pretty cool right here.
Those are not as far away as they possibly can be.
Oh, okay, so I can go like that.
No.
That looks like Mickey Mouse.
Kind of.
Actually, so if I want to put them as far away as possible, obviously you realize I can put them completely
There you
opposite
go. And-
in a linear triatomic fashion.
Right. Triatomic meaning
And
3 atoms.
In 3 atoms in a line, you
Lord.
see. And so that's why we have this concept of linear triatomic. They are at 180-degree bond angle. So the shape that is drawn in your paper is this shape right here, the linear triatomic shape. Looks like this, where the bond angles here are 180 degrees. So I have 2 clouds. This is the only shape with 2 clouds that's important. So now let's jump and talk about a 3-cloud type of a shape, okay? So now, back on the screen here, I need to get these as far away from each other as I possibly can. I don't think I've done a very good job. All right, Mr. Sams, how do you think we could fix that?
Make it kind of like a Y.
A Y.
Yeah. There you go.
And I want them ultimately probably like that. This shape right here is a plane.
Yep.
It's in one flat plane, right? And so it is, and these bond angles, what are those bond angles
Those
there?
would be 120 because they're going to add up to 360.
Yeah, and so it's in one plane, and they are as far away as they can possibly be.
Yep.
This shape is called
Trigonal planar.
trigonal planar. So the bond angle is 120 degrees. They're as far apart as they possibly can be. And so that shape looks like this. This is the trigonal planar shape, and each of these are 120 degrees. And it's in a plane, hence the word planar, trigonal planar.
Amazing how that works.
Now we can look at the trigonal planar. Mr. Sams has sort of a more professional model than the one I was building with my styrofoam balls. But
All
you
right.
can see, go ahead.
Yeah, another trigonal planar one here. So this is one that has a central atom and then 3 atoms coming off of it. So 3 clouds coming off. Now, its close related cousin here is we can take a trigonal planar, and I'm going to use my little tool to get this popped off of here. This is kind of fun. There we go. And we can pop one of those off, and we can replace it with a cloud of unpaired electrons.
So that thing sticking out that's sort of tan in color, that looks like a, I don't know what it looks like, it is the cloud of electrons, and that shape is a little bit different, okay? All right, bring
So it's
back
still
Mr.
related
Sams.
to the trigonal planar.
And I can do this with my styrofoam balls, although not nearly as good. Where now you can see the stick that I'm holding is that extra cloud, and this shape is now what shape?
That's going to be bent. Okay.
So,
if you're asked to draw draw a bent 120, this is what it would look like.
Now, basically, also, when you have three clouds, you're most likely going to have, like the example we just did a little bit ago, was nitrate has a double bond and 2 single bonds. You know, we draw the structure, trying to get all the electrons in there. That, of course, has 3 clouds.
Right.
Because one cloud, that's a cloud, that's a cloud, that's a cloud. Now, that's actually I did the wrong one. That's the trigonal planar one.
Right.
If I was to do SO2, I'll just give you an example I happen to know. SO2 looks like this. And so SO2, sulfur dioxide, has the same shape as this because it has this extra pair of electrons right here, which are these, which were the cloud we were showing you in it. And then it's got that. This is actually one of these is a double bond, but actually it displays resonance, etc. All right. So our next, so that's 2 clouds. So you should understand that if you've got 3 connections, it's trigonal planar, and it's bent 120 if you've got, you know, the extra pair of electrons. You know, you got X. It's going to look like that. Something like that. All right. Now, what happens if you have 4 clouds? When you have 4 clouds, now the goal on 4 clouds, let me see if I can get the elements or the atoms as far apart as possible. So now if you look on the screen, folks, I want to get my balls to stick together. Didn't sound very good.
We'll edit that out later.
Yeah, okay. I want to get them as far apart as I possibly can. So they keep falling off. I want to put them as far apart as possible. So I put them all at 90 degrees, and that looks like the best I can do, right?
No. Think 3-dimensionally. You're thinking on a plane here.
Yeah, and a lot of students, actually, I did this on purpose, folks. The mistake everyone makes is they think in 2 dimensions. The reality is that this is a 3-dimensional problem. Mr. Sams.
So back to Mr. Dog Toy here. This is my tetrahedral dog toy. And so if you have a central atom here in the middle, you've got one going up, one going out toward you, and then 2 going out to the back. And these bond angles are 109.5 degrees from one another. Tetrahedral shape.
I made one too, see?
Hey, look at that.
And I was able to do that. Or we actually have the very professional molecular
plastic
model
guys here too. So we've got, yeah. I see that. Did you guys ever see the old Willy Wonka show? The original one with the creepy Oompa Loompas? Yeah, that's what it looks like a gobstopper, does it not?
Oh, yeah. That's a gobstopper. There you go. So
right.
that's the tetrahedral shape. Now, our sticks make it look like the atoms are far apart, like in my model right here.
Yeah.
But Mr. Sam's, the little professional model, actually is a more realistic
model. Much more,
model.
yeah, close together. And they're actually even kind of more overlapped than this.
Yeah, that's true. So if you look at this screen here, this is your tetrahedral shape right here. These dashed lines, by the way, the dark line means it's coming out at you, and then the dashed lines are behind the plane of the paper, if you will. Hard to draw a 3-dimensional object on a 2-dimensional piece of paper, but that's kind of the best that you can do.
I have trouble drawing 2-dimensional objects on 2-dimensional paper.
Now this assumes that you've got 4 bonds, 1, 2, 3, 4 here. But sometimes you could have 4 bonds and only 3 connections, right?
That's true. So let's go back to our little model here of the plastic balls. So on our model here, we've got 4 atoms coming off the central atom.
Yeah, I see that.
Okay, so what I'm going to do is instead of one of those atoms, I'm going to replace that with an unbonded pair of electrons. So there are still 4 clouds, it's just 3 of them happen to be atoms down here, and one of them is an unbonded pair of electrons up here on the top. So this is derived from the tetrahedral shape, but we don't call it tetrahedral, we call this trigonal pyramidal.
Or pyramidal.
Pyramidal.
Or you can just call it pyramidal, because it looks like a
pyramid.
All right. And the way that we look at that, of course, is this is the picture right here. So you can see it looks like a pyramid right here, the base of a pyramid, a triangular pyramid. The bottom is a pyramid and these extra pair of electrons. I also want to say something interesting about this. The bond angle down here is 107 degrees.
Right. It's a little bit less than the 109.5 that we had on the tetrahedron.
On the tetrahedron, this bond angle is 109.5. Now, that's an odd thing. Why did the bond angle switch?
See those 2 unpaired electrons up there?
Yeah.
They like to repel each other, and then they also like to repel the electrons on those atoms.
But don't these electrons, this is 2 electrons, this would repel too.
Yeah, but those are kind of in a bond. Those unbonded ones, they like to fly around and they just like to repel other things, and they smush them together as a result, the other ones.
Let me give you another explanation. That's a good way to think of it. I've always thought of it a different way, Mr. Sams, actually. Right. This atom, whatever it might be, has a positive nucleus.
All right.
And he is drawing these two electrons, because remember a bond is two electrons. He's drawing those electrons closer to him.
All right.
These electrons, the unshared pair of electrons, the unbonded pair of electrons, they have no positive charge up here to push them up. And so they, for all intents and purposes, take up more space because they don't have the additional attractive force of the nucleus of the other atom connected to it. And so, I mean, probably the takeaway is that unshared pairs, actually write this down, unshared pairs have, or maybe say take up more space.
Yeah, just like we had the little plastic model, the unshared pair takes up a lot more space than the little atom does.
Then more space than a bonded pair.
Yeah.
I'm trying to think of the words. Okay? So that's going to happen when we go to our next shape.
Okay, so here was our trigonal pyramidal shape. We got our 3 bonded atoms on the bottom. We've got our unbonded pair on the top.
That's the pyramidal shape.
So I'm going to pop one of these atoms off of here again, and I'm going to replace it with another unbonded pair. And again, notice that the unbonded pairs take up a lot more space than the bonded pairs do. So this one now is still derived from the tetrahedral shape, looks a little different. We're going to call this one bent 104.5 because you can see if you ignore the unbonded pairs, let me just pop them off here, it's bent. And if you flip it upside down, it looks like Mickey Mouse.
Yep.
Hey, look at
this is the Mickey Mouse monocle.
This is the Mickey Mouse. Now, our perfect example of this one is water. This is how water looks.
All right, let's go back to the screen now. So this would be the bent 104.5. And again, remember the unshared pairs, they take up more space. That's why we now go from 109 to 107, now to 104.5. And water, the classic example, Mr. Sams was drawing water, looks like Mickey Mouse, where this bond angle here is 104.5. Now, don't get this confused. We also have the other bent one that looks more like this. With, you might think of it this way. I'll put extra electrons on it. One has 2 unpaired. This is bent 120 because there's only 3 pairs, effective pairs, 3 clouds. This is a 4-cloud species. Okay, now, you've before only learned about 2, 3, and 4 cloud species if you were in class last year. Now we want to learn about ones that violate the octet rule. So these are going to be trigonal, or they're going to be 5 cloud species. So folks, I've got my molecule here and it's all kind of discombobulated. The goal is to keep them as far apart as possible.
Discombobulated?
Yeah, that means they're not like all together.
I like that word.
You like that? Okay. So I need to get them as far apart as possible. So it's all messed up. I got 5 outer atoms and I need 5 clouds. And so what you actually do is let me show you how it's best. The best way I know to build these is you actually build a trigonal planar. That's that 120-degree bond angle. So that's going to look like this. And then what I do is that on top and then on the bottom, I put the top and bottom atom. And so what you have here is if you look at this, this is a trigonal pyramid right here, if you can kind of see the angle. But I flip it upside down and I have another trigonal pyramid. And they call this trigonal bipyramidal. So it's a triangular pyramid twice.
Yes.
Bi means 2. Mr. Sams has the professional model.
All right,
now.
our nifty little plastic ones. Okay, so you can see we've got the 3 around the middle. They're all in the same plane, like Mr. Bergman started with the trigonal planar, and then 1 going off the top and 1 going off the bottom. Okay. Now, another thing with the trigonal plane, the bond angles are 120 degrees from one another, and then if I flip it up like this, these are all 90 degrees from one another.
So it has
right
2
there.
different bond angles,
2 sets
both
of bond
120
angles, right.
and 90.
Right, 120 around the trigonal plane, and then 90 for the 2 up and down.
And if we look at the screen here we can see our 90-degree bond angle, and then between here and between here and between here, that's 120 degrees.
Yep.
And this is the trigonal bipyramidal. You can look at your chart there. So what you actually should be doing is looking at the chart and trying to visualize this as we're attempting to do that with this videos.
Yep.
Now, if we take away 1 cloud, what happens, Mr. Sampson? My favorite shape in all
Your
the world.
favorite shape?
I love this shape.
Is this the seesaw one? Is
Yeah, I
that the one
think
you want
it's
to
the
see?
cool one.
All right.
All right, so let's zoom back to you and me. So as I just took off the top molecule, if you see the stick, it's hard to see, but there's a stick here. That's going to be my cloud. This looks like a seesaw. Let me take this, Mr. Sims, and so we can see. And you can. It's called the seesaw shape. Do you see? I can seesaw.
Teeter-totter.
Teeter-totter. Some people actually call it the teeter-totter shape.
That's what I always
So Mr. Sams is going to show it to you in the professional model as he
Yes.
attempts to build it.
All right, so Here we go. Now, again, we're not taking the top or bottom one off. We're taking one of the ones off of the trigonal plane off of there. And so, yeah, let me get the book out again. You can see mine can teeter-totter.
Teeter-totter.
Back and forth, just like you did in 3rd grade, 2nd grade, or whatever you teeter-tottered. And so, yeah, it's one of the ones off the trigonal plane. That's the one that turns into the unbonded pair.
So back on the screen, the key thing to understand here, folks, is you've got 5 clouds and 4 connections. And 1 unshared pair. Unshared pair. Un-P. I don't know, whatever. Unshared pair. So this is the seesaw shape. All right. The next one, we'll just go on the screen here. If you take away an extra pair, it's going to now, or an extra bond. You still have 5 pairs, but now you only have 3 connections. This is the shape, and we call this, Mr. Sams, the
T-shape.
The T-shape.
Because it's shaped like a T. So, again, we're popping another one off of that trigonal plane. The top and bottom ones are still there. But if you look there, if I hold it straight at you, what's that look like? It looks like a T. Okay? T-shaped like that.
And you can see mine as well in the bigger sphere of influence here.
Yep, and all the angles here, these are 90-degree bond angles between here, and then we've got a 180-degree bond angle from this one to this one. Okay?
Yep.
And these are our unbonded pairs that are just kind of hanging out there that we don't really pay much attention to in terms of the shape.
And lastly, folks, if we were to take off another molecule, and the one you would take off would be this one, you would then get the shape.
Okay, this one's back to a linear shape. So if you look kind of through there, we've got the central atom, we've got 2 coming off the side. All 3 of that trigonal plane have been removed and are there now as unbonded pairs. So we're back to the linear shape, just like the linear triatomic, except this time we have 3 sets of unbonded pairs of electrons coming off that central atom.
And here it is pictured on the screen. It's still linear triatomic, but you do have extra electrons here on the outside. Okay, well, we've done 5 pairs. There is also the opportunity to do 6 pairs. This is as big as it gets, so let's attempt the 6-pair orientation. Folks, as I'm building this, the way I would build this is I would do the shape that I made the mistake on earlier. I would make this square shape where they come off this way, and then what I would do is I would then add 1 on the top, and then I would add 1 on the bottom. And this particular shape right here, okay, if you kind of look at it, is where everything is a 90-degree bond angle. 90, 90, 90, 90, 90, 6 of them. And this is called the octahedral shape. Mr. Sams has a cool
We
dog
got a dog toy. Octahedral dog toy. I was in a pet store one day and I saw this and I just had to have it, so I did. So yeah, like you said, there's 4 here and then 1 coming up and 1 coming down. These are all 90-degree bond angles.
Yep, 90.
Okay?
90, 90, 90, 90, 90.
All the way around. Okay?
All the 90s.
So, and we have our nifty little square here, my gobstopper model. I think that's what I'll just call this now. And it's the same thing. You've got 90-degree bond angles all around. So you have a square plane in the middle, and then 1 coming out towards you, and then 1 going out to the back of that, no matter how you look at it.
And this is, folks, what it would look like. This is our octahedral shape. Why is it called an octahedral shape?
Because there's 8 sides of an octahedron.
Yeah, because there's 6 bonds, but there's 8 sides. So it's kind of a little confusing, I think. But it is, by shape, it is definitely an octahedron. Okay. Now, if we were to pull 1 off, the shape would look like this right here. So you pull off 2 electrons, and
the 2 electrons go away, and we'll just take the bottom ones off there. Doesn't really matter because it's all symmetrical all the way around. And now we've got this square plane here, and then 1 coming off the top. And we're gonna call this one pyramidal because it looks like a pyramid. If you actually put walls on the sides all the way up here, it looks like one of the 4-sided pyramids like they kind of have in Egypt.
And if you look at mine, same thing. You can kind of see it. And it's actually important. It's not a. There's another pyramidal one. This is the second pyramidal one. One was a trigonal pyramidal.
Yes, this is a square.
This is
pyramidal.
a square pyramidal.
Yes.
So this shape is called square pyramidal. Well, we can take another bond off, and when we take another bond off, we'll take the top guy off.
Okay.
And so when you take the top guy off, here's how it would look. And actually, this is a shape that we have actually already seen in a mistake.
All right, so if we take the top and the bottom one off, we're left with these ones that are on the plane, and we're going to call this a square planar. Okay, so Mr. Bergman made the mistake earlier when he built the square planar when we were going to, that led us into the tetrahedral model. But this time, since we have these unbonded pairs of electrons on the top and bottom, they're going to repel each other and line all 4 of those up into a square planar instead of allowing them to go into the tetrahedral shape.
And this is just what it looks like in the plane. It's planar since it's in one plane. It's a flat molecule and it's square. Okay? And so this is the square planar. Well, we can keep on taking more things off, Mr. Sam. So I think we're having too much fun playing with these molecular models.
Times.
And so if we jump up, if I take two more, I have a new shape. It's going to have 3 bonds and 3 unshared pairs. So
All right, so we've got 3 unshared pairs now and 3 bonds, and you'll notice it looks kind of like the T-shaped one that we had earlier. But this is a T-shaped one with a different number of unbonded pairs of electrons. So still T-shaped, but we have a different number of unbonded pairs, and again, there's still 90-degree bond angles there.
And here's my T-shapes, which is probably a little easier to see, those small ones. But you get the idea. So this is called T-shaped. Okay? And lastly, we can take one more pair away, and I think we get the idea here. We now have 4 pairs of electrons along the central atom, unshared pairs, 1, 2, 3, 4, and 2 bonds, and we are back to a shape we've seen before. This is called linear triatomic, because you have 3 atoms in a line.
3 atoms in a line. We've got 4 unbonded pairs of electrons in there, and the bond angle here, again, is 180 degrees, just like all the other linear triatomics as well.
So you can see mine right here, and the same thing, linear triatomic. Now, I think something about what Mr. Sam's, go hold that up closer to him again, is that people are seeing those clouds. Those clouds are the unshared pairs of electrons.
Yes.
But the things that are in the line are the yellow and the green.
Yes.
The green are the outer atoms, and then the yellow is the central atom. The other things are just the extra pairs of electrons. But it's still, we only look at the atoms to determine the shape, not the clouds, although the clouds help determine the shape, if that makes sense.
Yep.
Okay? So, folks, that's the summary of the different shapes. All right. Should we do an example of shapes and polarity?
Probably should.
Yeah. So let's do an example, a couple examples. So what would be a good one we could do? Let's do maybe one that's kind of an odd shape.
Do you want me to build them too?
No. So let's do ammonia. Ammonia is NH3. Now I'm just going to draw the Lewis structure for you because you've learned how to draw the Lewis structure. If you draw the Lewis structure of ammonia, you would find that it looks like this. Now how many clouds are there, Mr. Sanders?
4 clouds.
4 clouds.
3 bonded pairs and 1 unbonded.
So if you have 1 unbonded pair, then the shape would be, so we're back here, and so you have 4 clouds, and you have 3 unshared pairs. You're going to be pyramidal, right?
Yep.
All right. So that's what we're doing. And so the shape of this, we'd write would be pyramidal.
Yes. So there's the shape. Now let's look at it in terms of polarity.
Well, polarity, remember, some shapes are ones that cancel out, and ammonia, and some don't. Ammonia, because it's a pyramidal shape, the center of the hydrogens is in the middle. So this one would be polar.
Yes.
Because it is not a canceling shape. Also, if you look at that slide that we just looked at a minute ago, we notice that we say that it is usually polar. Pyramidal shapes are usually polar. Very rare that it would not be polar. So you actually note here, they'll say if they're usually polar, actually this is the whole box here. Usually polar versus, this one's usually polar, but this one, say for example, is usually non-polar. So let's do another example. What should be another example we should do, Mr. Sams?
Oh, let's see. Let's do a
PCl5. How about that?
Yeah,
PCl5, phosphorus pentachloride, and I'm just going to draw the Lewis structure. You can draw it yourself. 3, 4, 5, and you put 2 electrons around, or 6 electrons, pardon me, around each chlorine atom. Now, how many clouds around this one, Mr. Sams?
There are 5 clouds around phosphorus.
5 clouds, and with 5 clouds, are there any unshared pairs?
No, there's not on this one.
Yeah, so this one would be the sort of the father of the family. I like to think of it as families. Yep. So this one, if we go back to our shape paper, is 5 clouds with all connections. So he would be
trigonal bipyramidal.
So trigonal bipyramidal? Pyramidal, man!
Pyramidal.
So this one would be trigonal bipyramidal. Okay, polarity.
It's non-polar. They're all going to cancel out.
Yeah, this shape cancels out. If you get the fathers of each of the families, if you will, they all cancel out. So they're all going to...
that's assuming all the things coming off are the same.
Yeah, that is something that's important to know to understand that. Okay, so that's that one. And let's do another example. So let's do another one, a xenon tetrafluoride.
Xenon?
Yeah, xenon's a noble gas. And you know what? If you ever are... You said tetra? Oh, yeah, okay. If you were... xenon's an odd one because if you ever are near a compound that has a noble gas and it's a compound, you need to get to the next county.
Yeah.
It's very, very unstable. All right, for xenon tetrafluoride, it would look like this. It would have 4 extra electrons around the xenon.
Yep.
So now, how many clouds around the xenon?
Xenon has 6 clouds, 4 bonded ones and 2 unbonded ones.
Okay, so if you look at your shape paper, then you have 6 clouds, and you only have 4 connections. In fact, xenon tetrafluoride is the example. So this is the square planar. And those shapes, they cancel out. They are at 90-degree bond angles.
They are.
And so that would make it a non-polar substance. So this would be, I'm going to write it now here, square planar and non-polar. Now we should talk about at least one more kind here. And let's say I have CClHH.
Yeah.
There are 4 clouds around the central atom. So this would be a what shape?
Tetrahedral.
Tetrahedral. Now get your shape paper out. If you don't have your shape paper out, you're in trouble. Tetrahedral. And it says usually nonpolar.
Right, usually.
And
that's
this is
assuming everything is the same coming off the central atom.
So this is a different ballgame because you see chlorine right here has a high electronegativity.
Right, much more so than hydrogen.
In fact, I think it's like 3.0-ish, maybe
Yeah,
3.5.
3.5.
I know hydrogen is 2.1.
Yeah.
So he's going to draw the electrons up closer to him. So the shape cancels out, but because you have a different external atom, you're actually going to draw it like this, and it's going to be a polar molecule because the chlorine is drawing. So when it says usually polar or usually nonpolar on the molecule that we were just looking at, or on the shape paper, that assumes that the exterior atoms are all identical. So in a case like this one, they are not all identical, therefore it's not polar. Or pardon me, it is polar. I didn't say that right. Okay, so
So it looks like we're done, Mr. Sands.
I think we are.
That was kind of a long podcast.
It was, but
Yeah.
you know, it's for conceptually not horrible.
Yeah.
Just go back to that shape sheet. That's the key.
I do, yeah.
Get you some dog toys, you know, play around with them. That way you can have octahedrals.
Can I take
in your
this home
house.
to my dog?
No, he'll destroy it. These are for chemistry.
Oh, they're chemistry dog
I've
toys.
seen your dog. He's big.
He is big. He likes to run.
Yeah.
All right.
well, ladies and gentlemen, viva el Siu!